Welcome to this video on oscillatory motion part 2. Our main objective in this video is going to be to take a look at what physical parameters affect the motion of an oscillating body. If you haven't checked out part 1, you want to check that out because a lot of those terms and ideas I'm going to revisit in this video. Again, I'm also using a PhET simulation from phet.colorado.edu, and there's a link to the simulation in the description below so you can play along. Alright, so let's think about first an alternate term for this word oscillatory. And this is actually a term I prefer to use because I think it is more descriptive, and this is periodic motion. Now that has this root word here, period, and a period, remember, is the amount of time that it takes to complete one of the cycles of the motion. So we think of the motion as broken up into periodic or period chunks that reoccur over and over again. So if I come over to the simulator here, I'm going to set it to 10 degrees and release it, and we see that it's oscillating through the equilibrium position, reaching a maximum amplitude on either end. Now they have a very cool period timer here, which will isolate the period of the time for just one period and map out the path, which we see there is 1.6816 seconds. So if we were to graph this on this first and fourth quadrant graph that I have here, we see that the object starts at an equilibrium position, that was the 10-degree mark, and it oscillates through equilibrium, reaches the other maximum amplitude, and this motion occurs again and again. Now, what we see here is there's two different perspectives that we can look at this. We can map out from the maximum amplitude through equilibrium to the other amplitude, and then back through equilibrium back to where it started, and we can call that one complete cycle. We can also call from equilibrium through equilibrium back to equilibrium a complete cycle. Both of those can be seen as a period, and in fact any position back through equilibrium to that same position again is a period of time. Now from the trig perspective for this graph, we can say that this is one complete cycle of a unit circle. So if we take the unit circle and we do one complete cycle, we know that that is 2 pi radians of movement. Now the time that it takes to make those 2 pi radians is t, which is the period again. This term over here is known as the angular frequency. Now the angular frequency has the same symbol as the angular speed or angular velocity, and they can be used interchangeably in some cases, but we have to be a little cautious. Technically the angular frequency will be the magnitude of the angular velocity, and we'll get into more theoretical discussion of that later. Now of course we know that we have an amplitude at each of these gaps from the equilibrium to the maximum position, and this could be a graph of velocity or acceleration or time because displacement, because the same pattern is occurring. Now let's see what happens when we adjust some things about this motion. But we're going to take a look at it not only from this experimental vantage point, but also in a more theoretical perspective based on the information that we know. So if I set this to 10 degrees and I release it, if I'm to adjust the mass here, I'm going to see that there's no change in the period, that it doesn't have any effect on the motion of this pendulum. Now keep in mind that we've said the string here is a negligible amount of mass compared to the pendulum bob, so that will have an effect later on when we look at it. Now if we take a look at adjusting the length, so let's make this, well, we'll start at our regular position. Let me go ahead and let this swing. It's 1.6816 seconds, and as I increase the length, I see that the period has increased. So it seems like the length and the period are at least directly proportional. But if we were to actually graph these values, we would see that it's not increasing by the same amount every time, and in fact it's going to increase by less as we lengthen this string. And so if we were to graph the period versus the length, we find that we will have a square root relationship. So we're going to say that t is proportional to the square root of L. Now let's think about this from the perspective of moment of inertia, the rotational inertia of this point mass on the end of this string. Now remember, that's the resistance to the change. So the force is applying a pull, if you will, or the force of gravity is applying a force at this point, which is x distance or L distance away from the axis of rotation, and that's causing a torque, a restoring torque on this object. So not only is there a restoring force, but there's a restoring torque as well on this object. Now we know that torque is equal to I alpha, I being the moment of inertia, and the moment of inertia is affected by this distance from where the mass is located to the axis of rotation. Therefore, it's going to affect the motion. Now you might be thinking, well, moment of inertia also includes mass, mr squared includes mass, so how come the mass isn't affecting it? And we'll see that the mass actually cancels out if we are to write the torque expression F cross R, here F being mg cross R, that distance, and we know that I alpha is also equal to this, which is torque. So we see that mg cross R equals mr squared times alpha, and the m's actually factor out of the whole thing. Now we can see here that we will have something, g will have an effect, and that effect is what we're going to look at next. Now if we think about it, the stronger the g is, the greater the torque is, and then the greater the angular acceleration. Thus, it will pull this little mass faster, so there will be a greater acceleration. So let's go ahead and check that out. We'll put it at 10 degrees again, hit play, and as we increase the gravitational pull, and we approach here the gravity of Jupiter, which is around 25 meters per second squared, we see that it is indeed moving faster. So let's just double check here on the period. Yeah, it's substantially less than 1.6816, which is what it was for Earth. So if we were to graph the period versus the gravitational field, we would see a t is proportional to 1 over g, like this, the square root of 1 over g. And so if we were to put both of those proportions together, we'd see that t is proportional to the square root of L over g. And we're going to take a look at how we can actually prove this theoretically in a later video. Now, one thing that we want to look at here is that the angular frequency is 2 pi over t. And we've got t over here, so let's see if we can relate 2 pi radians to this expression. And so what's going to happen here is, because we have the inverse of t here, we're going to set this equal to the inverse of that equation. Now when I solve for t, what I end up finding is that t is equal to 2 pi times root L over g. So when I divide, or when I multiply by t on both sides, then divide or multiply by root L over g, the reciprocal, and move it around, I get an expression that looks like this. And that is, in fact, the equation that would determine the period of a pendulum that is oscillating back and forth. Now keep in mind that this is a simple pendulum. And a simple pendulum is different than a physical pendulum because the mass of the string is negligible compared to the mass of the bob. But as this mass approaches the mass of the bob, then of course our moment of inertia is going to shift, and that's going to change the way that the equation is set up. And we'll look at that a little bit later on. In the next video, we're going to take a look at an oscillating spring and see if we can set up the same basic ideas, but for the spring rather than the pendulum.